Usually when these announcements happen, they go like, well, like, we have this thing like, and then you like apply, and it's totally awesome. And I enjoyed that. That was great. All right. So talking about things that are like totally awesome, we're going to talk about a really difficult set of concepts today. Your neighbor is angry at you if you're talking to your other neighbor. All right, good. Thank you. So today's a pretty rough lecture, especially towards the end. So deep breaths. If you were going to have your granola bar halfway through the lecture, maybe front load the carbs, because it's going to be tough today. Not that tough, but there's a lot of stuff. All right. So what did we do last time? We talked about what individuals do, right? We know by now, and we believe, Max, that individuals, or the vast majority of individuals, no more talking, please. I don't care, but the person sitting next to you trying to listen cares. That the vast majority of individuals tries to make themselves as well off as possible in the face of scarcity. Now that we're economists, nerdy, badly dressed, terrible sense of humor, what that means is individuals maximize utility subject to a budget constraint. What we showed is that the indifference curves that come straight from the utility function at the optimum can have two sort of outcomes here. The first outcome is an interior solution at the optimum, where you consume positive quantities of both goods, and we showed that for imperfect substitutes. That's equivalent to saying that the marginal rate of substitution is equal to the marginal rate of transformation, or spending $1 more on either good gives you the same amount of additional utility, so you have no incentive to move in either direction towards Hershey's or Reese's. That was an interior solution. Then we started talking about these crazy corner solutions. If your indifference curves or your preferences are consistent with perfect substitutes or these quasi-linear indifference curves, what you can actually get is you can get scenarios where you're consuming only one of the goods. Right? We live in a two-good world right now. That means you consume positive quantities of one good and zero quantities of the other. In reality, what we've got is you consume thousands of goods, or you could consume thousands of goods, but you consume zero of a vast number of them. Right? Who really eats kale? Come on. Lots of people up here with kale chips. Not for me. So the point here is what these corner solutions show you is actually a nice reflection of reality where we in equilibrium make ourselves as well off as possible by not consuming certain things, right? A corner solution. Then what we did is using imperfect substitutes, we derived demand, right? What's demand? Demand tells me the optimal quantity demanded at different levels of prices. So we used a budget constraint, held income fixed, held the price of Reese's fixed, and varied the price of Hershey's, right? Went from very expensive Hershey's to a lower price of Hershey's to ridiculously cheap Hershey's, and looked at what the optimal consumption bundle is for these different prices, and then plotted the optimal quantity of Hershey's against these different price levels and showed that the higher price, the lower the quantity of Hershey's consumed is. That got us a downward sloping demand curve, which makes sense. If prices for stuff go up, you generally demand less of it. We're going to talk more today about the unicorn good, which is the so-called Giffen good. Economists argue that it exists, but nobody's ever seen one in the wild, right? If you've ever seen the movie Up, that's sort of what we're talking about here. But those are goods where if prices of things go up, holding everything else constant, people consume more of it, right? This is not that people wanting to consume more of a product that is more expensive, right? You could see that some people like to spend $25 million on a watch to signal that they're oh so wealthy, right? That's not what I'm talking about here. What I'm talking about here is if you take one type of good, take a Swatch watch, right? And you start ramping up its price, and as price goes up, people consume more of it, right? That's a Giffen good. It's not different goods that have higher prices, and people sort of sort towards the consumption of higher price goods. So who does that? Who consumes more of something as the price goes up? I'll talk about that a little bit more. There's some evidence in the art world and other goods, other places where we've seen some evidence of this, but I still don't believe it. Then we talked about something called the Engel curve, named after a very famous economist. His last name's Engel. I'm going to put out a prize, $5 for the person who comes up first to me next lecture, not today, and tells me what the person's first name was and where they were born. All right, $5. So famous economists. You need to know their faces. They're all good looking. So Engel basically said as income levels change, we also change our consumption patterns, right? We see this. We live in the wealthiest society that mankind has ever seen today, right? There's never been in the history of humanity this level, ridiculous level of wealth. And I'm not talking about this discussion of the 1% here that's been going on for the past year or two or five. But I'm talking about overall, as a society, even the poorest of the poor likely are better off today than the poorest of the poor were 100 or 200 years ago, right? We consume different consumption bundles today than people did 50 or 100 years ago, and a lot of that has to do with the fact that incomes have risen in real terms. I'm not talking about inflation, but in real terms. So what Engel wanted to point out is what happens to my optimal consumption of Hershey's, not as the price of Hershey's changes, but as my incomes go up, right? As I have more money to spend, do I consume more Hershey's or do I consume fewer Hershey's? And we're going to dive into that in some more depth today, but this got us to this notion of normal versus inferior goods, where if a good's normal, you have more income, you're going to consume more of it, right? Versus if a good's inferior, as you get wealthier, you're so glad you no longer have to consume cup of noodles, you're only going to consume truffle-crusted filet mignon served on, I don't know, a bed of rare seaweed or something like that, right? I've seen that happen. It was, but the point here is demand plots optimal quantity demanded against price. Engel curve plots optimal quantity demanded against income. They're two fundamentally different things. So last time I sort of ended with this particular slide here that talked about elasticities. Elasticities are awesome. They're not just useful in economics, they're useful everywhere. They're especially useful if you're trying to make a convincing argument. Right? If you need to spend in a 5-minute presentation 60 seconds of your time explaining what the impact of a change in one variable is on another, and then saying this is a big deal because this is measured in these units, this is measured in these units, and hence it's a big deal, if instead you can say a 1% change in this variable causes a 6% change in the other variable, or the elasticity of y on x is 6, you're done. In 5 seconds or 10 seconds, everybody understands what you're talking about and can judge whether that number is a big deal or not, and it's a very, very effective way of communicating sensitivity of one variable with respect to changes in another variable. I've had caffeine again today, so I'm going fast. Yesterday I had no caffeine. The grad students all fell asleep. I got to sort of, maybe I should go half calf. All right. So elasticities are unitless measures of responsiveness of anything. Right? In economics, we often use them, or we most frequently use them, in this price elasticity of demand context, where we say, what is the percent change in quantity demanded due to a percent change in price? Right? If price changes by a percent, what happens to quantity demanded in percentage terms? That's the most common usage of this. So here's a nice little formula for you. We all love formulas because they're great. So that's what, fancy. Elasticity is an epsilon. It's Greek. You all know we go fancy when Greek letters appear. That's pathetic. But epsilon generally means the elasticity. QD here is quantity demanded, and then the thing next to the comma tells me with respect to what. So this notation here simply means the elasticity of quantity demanded with respect to its price. Okay? So in words, what the elasticity means is the percent change in quantity demanded due to the percent change in price. Now you're hoping I'm going to stop there because you can understand that. But I want to go here. That seems frightening. There are triangles that could be Greek letters, and there are now 4 things here instead of just 2. So let me try and walk you through where that comes from and why that particular formula here is useful, and then we'll apply it too. So let's use this misbehaved Microsoft Surface here and try and get to this formula. So when you're thinking of deriving a percent change in anything, right, the percent change in quantity demanded, right, the percent change of anything is just the change in the quantity divided by what the level is. I'm going to give you an example in a second, but let me write that down before I forget it with my rapidly aging brain here. So what do I mean by that? The percent change in quantity demanded is the change in quantity demanded over quantity demanded, right? So if quantity demanded goes from 100 to 110, the percent change is, well, how much did it go up by? 10, divided by what we began with, 100. So it's 10 over 100, it's 10%, right? Or 0.1. So that's how we define the percent change in quantity demanded. That's the numerator. The denominator, of course, is the same thing here, only now we're talking about price. The percent change in price is the change in price over price. So what do I mean by that? If price before was $1, now it's $1.05. Price changed by $0.05 or 5 cents. Price to begin with was $1, so the percent change in price was 5% or 0.05. Right? So I'm just writing out percent change as a formula. Now what I'm going to do is I'm going to do something crazy. Remember in kindergarten when you learned fractions of fractions and you freaked out because stuff was sort of flipping and you forgot where it flipped to? Yeah, I freaked out too, but I remember how it worked. So I'm going to do exactly this here. I'm going to draw a fraction through here, and what I've got now, right, is I've got this here, but now expressed as a fraction of a fraction. Exciting. So let's rearrange this. All right, here's how I remembered this when I was little. In Germany, you do calculus in preschool. I'm kidding. So let's look at this fraction, right? Numerator, denominator, that's my numerator. And then my denominator is a numerator and a denominator. So the way I remember this is, right, there's this big delta QD sitting on top of this poor little QD guy right here. So he says, I'm not going to let that happen, and he drops to the bottom, right? And this little p down here has 3 things sitting on top of it. He's really smart. So he's going to do, I'm going to sneak out of here, and I'm going to sit right on top. All right, so he sneaks out. P goes here, and delta p stays here. Trust me that this is right. So what I've got now is the change in QD. Oops, this is supposed to, no, that's right. Change in price times price over quantity demanded. Okay, so that's this formula right here. Right? Unfortunately, I already wrote it out here because I don't know how to zoom things in and out with these equation editors. But this thing right here, this expression here, is the change in quantity demanded due to a change in price. That's just the slope of my demand curve, right? So the elasticity is simply the slope of the demand curve multiplied by the ratio of price over quantity. So if you had a demand curve, right, what you could do is you could figure out what its slope is. We know that, right? You just figure out the slope of a straight line, and you multiply it for any price-quantity combination on that demand curve by the ratio of price over quantity. And we're going to practice that in a minute. So this elasticity, how price-responsive demand is, depends on 3 things. It depends on the slope of your demand curve, meaning how steep or how flat it is, and it depends on how big price and how big quantity is on that demand curve, where you are on that demand curve. So that's pretty exciting. We're going to deal with this in a second. I want to give you the 2 extremes, right? So we have very elastic demand curves, and we have very inelastic demand curves. We have relatively elastic and relatively inelastic and unitary elastic, and we're going to have so many elasticities, our head's going to start spinning. But let's start with the 2 extremes here. Now, what I would like to do is I would like to sell someone in this room a quarter. I forgot to bring a quarter. Josh, do you have a quarter? Or a dime or a nickel or something? All right, excellent. Thank you. See, I hired the best GSIs. They're clearly overpaid because he's got a quarter in his pocket. Thank you. I'm joking. The most underpaid people in academia are GSIs. So here's a quarter that doesn't even belong to me. I would like to sell you this quarter for $150. Anybody here like it? Really? Why? Why do you want to pay $150 for this quarter? You don't know, right? You just want to raise your hand. All right, I'm sorry. I'm just, okay, how about $50? No way. Who buys a quarter for $50? This wasn't owned by, Abraham Lincoln. This was owned by Josh. He's a cool guy, but come on, $50 for something that's worth 25 cents? Not doing it. How about $1? How about 50 cents? The thing's worth 25 cents, right? So how about 26 cents? No way. Anybody here want to take it at 25 cents? All right, sure. All right, so we've got one taker for 25 cents. How about if I give it to you for 24 cents, and you can buy as many of these as you want from me for 24 cents? Come on, yeah, here's one guy who's figured out the arbitrage opportunity, right? I would like to buy $1 billion worth of quarters from you for 24 cents a piece. I will turn around and sell them for 25, and I've made a ton of money in an arbitrage opportunity, right? So the point I'm trying to make here is, here's a good that's worth exactly 25 cents. Above the price of 25 cents, nobody's willing to buy it. And below the price of 25 cents, people are going to buy as many of these as they possibly can because they can turn around and sell them for 25 cents and make whatever, the spread is between the value of the good and what I'm willing to sell it to you for. So you go from being able to sell none of these at prices above 25 cents to being able to sell as many as you possibly want at a price of 25 cents or lower. So this is a little bit like, for those of you who've seen that movie Star Wars, but you're probably too young for that. I'm kidding. Who hasn't seen Star Wars? Come on. The first time Han Solo gets in the Millennium Falcon, you're like, what's going to happen next? And then he was it, and he gets to the Kessel Run in under, 2 parsecs? You go from 0 to infinity at 1 point, right? From being able to sell 0 to being able to sell as many as you want. So that's a perfectly elastic demand curve for a good. So I use 25 cents, but, let's use something that's worth $5. That perfectly, I'm so excited I'm out of breath. Maybe it was the climbing of the 4 stairs. It's a perfectly elastic demand curve here. So if you wanted to be strict here, the demand curve actually goes from, at higher prices here, you sell 0 units, and at any price of $5 or below, you can sell as many as you want. So the point here is you go from 0 to being able to be willing to buy as many units as you want here at 1 price. So that's a perfectly elastic demand curve. How about a perfectly inelastic demand curve? So my grandfather was insulin dependent, right? He had to inject insulin into his leg every single day for 40 years or something like that. His life depended upon the ability to inject insulin into his leg. Berkeley, of course, did a lot for insulin production, so you should read Randy Schekman's biography. He won the Nobel Prize recently, so read that because you're going to Berkeley and you should know what your Nobel laureates do. But the point here is he didn't really care how much this stuff costs. If he didn't get 1 shot a day or 2 shots a day, he would die, right? So he would essentially be willing to pay anything he could for that particular unit of good every single day. So he's perfectly price inelastic, meaning he would pay whatever he could for the quantity he required. So the perfectly inelastic demand curve looks the exact opposite, right? If you need 5 units a day, your demand curve is a straight vertical line at 5 units. So that's perfectly elastic, that's perfectly inelastic, right? Those are the two extremes. Well, what about reality? What about the in-between here? Price elasticity of demand for most goods and most individuals is actually not, infinity or not 0. So perfectly inelastic means your price elasticity of demand is 0. Perfectly elastic means it's infinity, right? Because you're dividing by 0, and that's infinity. But in between there, there's a big number. There's a big set of numbers between 0 and infinity. And price elasticity, of course, is negative, so we're talking here about absolute values. So 0 means perfectly inelastic. Infinity means perfectly elastic. But in between, we categorize the elasticity of demand into 3 buckets, right? Relatively inelastic means, you're not that price responsive. You are price responsive, but not very much if your price elasticity demand is between 0 and 1. Right? Examples of this are things like electricity demand. One of our graduate students here wrote maybe the seminal paper on residential electricity demand, and he argues that the price elasticity of residential electricity demand is somewhere between 0.2 and 0.5, right? So if electricity price goes up by about 1%, your consumption of electricity goes down by about 0.5%. That's relatively inelastic. Then the opposite of that here are relatively elastic things, where your price elasticity of demand is somewhere between 1 and infinity, 5, 7, 9, 12. Things that are relatively price elastic are luxury goods, for example, right? How price elastic are you to soy lattes at Starbucks, unless you're addicted to them? Probably pretty price elastic, right? If Starbucks raises its price of soy lattes by $1, which they basically did, right? Soy milk used to be free for a long time, and then they decided that wasn't a good idea, so then you had to pay for soy milk if you had their little membership card there. That changed my consumption pattern of soy lattes, right? 70 cents a day, do the math, per year, that's a lot of money, right? That's $200. So now I have my soy milk at home. But the point here, luxury goods, handbags. My sister she works in luxury goods. She's a consultant, so she has the very unfortunate burden of having to show up at clients with really fancy handbags, which she really hates, right? So she gets to go to like Bloomingdale's and buy fancy handbags all the time as a professional hazard. Terrible, terrible fate for her. But the point here is most individuals, fancy handbags, fancy watches are often relatively price elastic goods. Then there's one special case here which really doesn't have a meaning except for it'll come in handy when we're going to talk about the monopolist. It's unitary elasticity. If a 1% change in price leads to a 1% drop in quantity demanded, that means you're unitarily elastic, right? You're somewhere in between relatively inelastic and relatively elastic. It just means your elasticity is exactly -1. So that's the table. You don't necessarily have to memorize it, but I'm going to use the words relatively inelastic, perfectly elastic, and unitarily elastic a lot, so you should know what they mean. But there's no real intuition hidden in there, except for the price elasticity of demand goes from 0 to higher and higher and higher as we go down this particular table. Okay, now Max, that was kind of cool. I enjoyed that little ditty there with the perfectly elastic demand curve. That was entertaining for a Thursday morning. I also enjoyed the insulin example. I could get that, right? But most demand curves aren't perfectly elastic. Most demand curves also aren't perfectly inelastic. So what about the regular old demand curve, right? In the demand and supply model, that straight line that starts somewhere in Seattle and goes somewhere to Miami, right? What does that mean? By the way, does everybody understand what I mean by Seattle and Miami? When I mean the graph here, I think of this as the United States, San Diego, Boston, Miami, Seattle, right? So instead of saying 10, 0, 0, 10, I use those as points on a graph. We can do Germany too if you prefer that, but your German geography is probably worse than your American one. So we'll stick with those. So is mine, actually. Okay, so let's talk about the regular demand curve here for a second. What does a regular demand curve look like? Well, Max, it looks like this. First of all, it's beautifully labeled. Quantity on the x-axis, price on the y-axis, and then this particular one goes from 8 to 8. Okay. Meet your demand curve. Okay, so the first thing I know is that the elasticity of demand with respect to price is the change in Q over the change in price times price over quantity. So the first thing I would like to know is what's the slope of my demand curve, and then I can figure out, for different points on the demand curve what the elasticity is. So here, I made the example very easy for you. What happens to quantity as price rises by 1 point? So start at 2, go to 3, raise price by a point. Quantity goes from 6 to 5, so it's -1. Right? What if I go from 4 to 5? Well, quantity goes from 4 to 3, again it's -1. So the slope of the demand curve here is -1. Now, I won't trick you with this, but somebody raised this last time and said, oh, slopes and economists are weird, right? You guys sort of flip the axes and then talk about slopes of a flipped graph. You're absolutely right, right? What's on the y-axis here? Price. What's on the x-axis? Quantity, right? What's the slope I'm talking about here? Am I talking about the slope of what I drew, or am I talking about the slope of the thing flipped? The thing flipped, right? So here it's easy, because the slope of this graph here is exactly -1, so no matter whether you switch these axes, it's always going to be -1. Just do a quick thought experiment here. What about, and I'm going to erase this, so don't ruin this beautiful picture, but I just want to make this point. What about this demand curve? So I've got price on the y-axis, I've got quantity on the x-axis. So if price rises by 1 unit from 2 to 3, quantity drops by a half unit, right? So the slope of this thing is a half. You can verify that here. Price goes from 5 to 6, quantity goes from 1.5 to 1.